Alright, so welcome to this first episode of just a series which I'm hoping I can keep going for a while, which is a series on interesting integrals. And so this is going to be the first video on that, and I'll just basically be looking at some interesting integral problems, and so one per video, so they should be relatively short. So you can watch any episode in the series in any order you want. I won't tend to use any previous results, and I mean that's mainly because I expect you to be familiar with how to solve regular integrals. So things like substitution, integration by parts, just splitting integrals in bilinear, partial fractions, all that kind of stuff you should be familiar with, because we're probably just going to be using it without dwelling over it in the videos. Alright, so for this one I want to look at the integral of x cot x from 0 to pi over 2. So it's a definite integral, so we're supposed to get some value at the end. We're not going to be looking for a function. So in the spirit of this being the first video, usually when you solve a definite integral, you'll first be looking to get the antiderivative, and then you'll use the fundamental theorem of calculus to, evaluate it at pi over 2, and then subtract its evaluation at 0. Thing is, x cot x does not have a nice antiderivative, and if you look at it, the antiderivative would be, and I didn't calculate this myself, I just plugged it into a Wolfram, but you'd get I times Lie2, and Lie is the dilogarithm, it's a special complex function, times evaluated at 1 minus e to the 2ix, all minus x squared, all that over 2, and then plus c, obviously. And, we're not going to be using this, because it's a very nasty antiderivative. It requires knowledge of polylogarithms, knowledge of complex numbers, which maybe you don't have, and so we're not going to be using this to try to get the fundamental theorem of calculus, and that's also because just getting this antiderivative is very tedious. So instead, we're going to try and look at some nice properties that we can exploit from this. And we're going to start by integrating by parts. So let's see what we get by integrating by parts, right? So if we integrate by parts, let's say that x is our u, and that cot x is our dv over dx. Okay? Oh, that's a weird drawing, whatever. So if I split it and integrate it by parts, then what I'll get is x times the integral of cot x dx, the indefinite integral, so the antiderivative if you prefer, evaluated at pi over 2 and 2 to 0, or 0 to pi over 2. And then from that we subtract our original integral, 0 to pi over 2, except now, we're going to have v, and v is the integral of cot x, times du over dx. And du over dx is just dx over dx, which is 1. Which is why we don't see it anywhere here. Now obviously this is really messy, and that's mainly because we have just introduced a new integral in here, which is the integral of cot x. So if we don't want it to get any more messy, we're going to have to evaluate that. Thankfully, that's pretty easy to evaluate. So you can, write, cotangent of x is just 1 over the tangent. The tangent is sine over cos, so the cotangent is cos over sine, like this. And then if you make the substitution u equals sine of x, then du over dx is going to be equal to cos x, such. And so that allows us to say that du equals, dx equals du times 1 over cos x. Not very neat, whatever. So when we substitute that, we've got u for sine, then we've got dx becomes du times 1 over cos x, so the cos x's cancel, and then we're left with 1 over u du. And the integral of 1 over u du is pretty simple to get. It's just the natural logarithm. It's going to be ln of u. And so that means we're going to have that the integral of cot of x is ln of sine of x, because we just resubstitute back in what u is. And note we have, these absolute values because that's how we get them in integrals. Thankfully, we're going to be able to get rid of those absolute values between 0 and pi over 2. Sine of x is positive all the time, so we won't have to worry about that. Alright, so let's keep going with this. If we plug it into our integration by parts, then we get rid of all those nasty extra integrals, and now we just have ln of sine of x, and I've obviously gotten rid of a constant because it's not going to help us out. Okay, so with that, if I evaluate the first parts, well, x at pi over 2 is just pi over 2, ln of sine of x at pi over 2, well, sine of pi over 2 is just 1, so we've got ln of 1, and notes I've changed into parentheses instead of absolute values because, 1 is already at an absolute value. And then from that, I'll still subtract our integral. Thing is, you'll note that ln of 1, well, ln is the inverse of the exponential, and e to the 0 equals 1. So that means that ln of 1 is equal to 0. And so we're only left with the negative integral from 0 to pi over 2 of ln sine of x. So that means we've showed that this is equal to that. And so now we've reduced the problem to actually finding a completely different integral, which is ln of sine of x, and that may be easier to actually find. So now we only have to actually solve that. But it's still not completely easy, and we still have to use some tricks. And so the main trick we're going to use is we're going to look at the graph of sine of x and cos of x. Let's look at that between 0 and pi. So we've got here, this is the line at pi over 2, and this is the line at pi. And so this one is sine. You can see that because it starts at 0, and this one is cosine. And you know that generally we want to be able to solve these by hand, and sure, I've used a program to generate this graph, but I mean the sine and cosine graphs are well known enough for you to draw these yourself. So the first thing we'd like to note, and honestly there's actually two things we'd like to note, and the first one is if I look at the area between 0 and pi over 2 under sine, right? So this area here. Well, that's the same as the area under cosine and the graph, because we'll see, you know, this section here is the same as this section there. And so that means that the integral of from 0 to pi over 2 of sine of x is the same as the integral of cos of x in that bound. And since we're applying ln to both of these, well, it's still going to be the same. We're still going to have the integral from 0 to pi over 2 of ln sine of x is the same as the integral from 0 to pi over 2 of ln cos of x. So that's a nice symmetry we can use. So that's the first thing we'd like to note. And also, well, that's the second thing we'd like to note, I guess. But the first thing we'd like to note then would be that sine of x is symmetric about pi over 2, and you don't really need the graph to know that. And that's going to be a pretty useful thing we're going to use as well. Alright, so now we use our second fact, our second observation. And so we have that the integral from 0 to pi over 2 of ln of sine of x dx is equal to the integral from 0 to pi over 2 of ln cos of x dx. Okay? And that's because these inputs here, sine of x and cos of x, they range exactly in the same way from 0 to pi over 2, so we get the same integral. So hence, now I can add this integral here to the whole equation, so I had to get 2 times this integral on the left-hand side, and on the right-hand side I've got the integral from 0 to pi over 2 of ln cos of x dx, and I can add to that the integral from 0 to pi over 2 of ln sine of x dx, and I can just put these integrals together because they have the same bounds. So we've got ln of cos of x plus ln of sine of x dx in one integral. And if you'll remember, ln of a plus ln of b, that's going to be equal to ln of a times b. And that's a standard log rule, which is just, you know, the inverse of a rule that e to the a times e to the b is equal to e to the a plus b. So now what we have here is that this is the integral of ln of cos of x times sine of x, and we've been able to combine these. And there's a extra parentheses here that shouldn't be there. Okay. And so now we can simplify that, because you might also note the double angle formula for sine of 2x. Sine of 2x is equal to 2 cos x sine of x. That's the double angle formula for sine of x. And so that means that cos of x times sine of x is 1/2 of this. So we've got ln of 1/2 sine of 2x. And so with that, now I can split it again by using the same log rules earlier, so that I'd have ln of 1/2 plus ln of sine 2x, and I can split the integral. So I get the integral of ln of 1/2 dx plus the integral of ln sine of 2x dx, with those bounds 0 to pi over 2. And so this one here is pretty easy to evaluate, so that's what we're going to do first. So we have that 2 times the integral from 0 to pi over 2 ln sine of x dx is equal to that split integral as I just showed. So now we can continue and evaluate this one here. So we get the same again, we have the same left-hand side. And this one, well, the indefinite integral we can actually get easily. It's just x times ln of 1/2. And so now if we evaluate that from pi over 2 to 0, then we've got that it's just going to be pi over 2 times ln of 1/2, because the 0 term is just going to vanish. And we've still got that second integral over here. And so now for the second integral, you know, we could just, well, we don't know how to solve this yet, but we can perform a nice substitution. And, you know, we can just say u equals 2x, and that means that du over dx is going to be 2. And so then we'd have that dx equals du over 2. And so we've got 1/2 of that integral now, and the bounds have changed from 0 to pi, because we had u equals 2x. And here I've written x, but I mean, you could, if you're more comfortable with that, you could write this as u, and here's u. but it doesn't matter because it's just the variable of integration. It doesn't actually matter what letter we use. Okay. So now we'll use our first fact, which is that sine of x is symmetric about pi over 2. And so we'll have that this integral from 0 to pi of ln sine of x is just 2 times the integral from 0 to pi over 2. And why is that? Well, if we look again at the graph of sine of x, which is something like this, of course, this is pretty bad, but whatever. Then we have the line x equals pi over 2 down the middle. Well, the area of the whole thing is the same as 2 times this area, which would be the integral of 0 to pi over 2. And when we apply ln to this whole graph, it won't change the symmetry, so we'll have the exact same thing. And so hence, we've got 2 times the integral to 0 to pi over 2 of ln sine of x dx. That was the left-hand side, it's still the same. This here hasn't changed. And so now we've got that 1/2 of the one with the bounds from 0 to pi just becomes the same as the integral we were interested in the first place. And so now, we've only got one final step to do. We can just rearrange and, subtract this from both sides. So we remove it from here and we subtract it here. And so now, that means that we've got this has gone to 1, and so we've got the integral that we're interested in is equal to pi over 2 ln of 1/2. And so now that we know how to evaluate this, we can finish off our original problem, just by plugging into our integration by parts expression. And so we'll have that the integral from 0 to pi over 2 of x times cot x dx is equal to minus pi over 2 times ln of 1/2. And so that's just going to be pi over 2 times ln of 2, because, the minus becomes a power inside, and 1/2 to the minus 1 is just 2. And so that's the answer we were looking for. And you see that, we didn't have to go for any nasty dialogarithms or anything like that. We just played with symmetry on graphs, and that's a technique you might want to use quite often when you don't know how to take an antiderivative. So I'll see you in the next one.